Okay, sorry about that. Little battery change issue. Okay, some quick announcements. So projects, I'm going to post. I was going to do it here, but we've got a lot to talk about. So we're going to post by tomorrow sort of the basic rules for how we're going to do the project presentations and final project submission. The other thing I normally do in class, which I love to do, is I have MATLAB open and I have all your names in a cell array and I do rand perm right in front of you and I have them start going backwards from the end and it gets slower and slower as it goes. But last time I had 22 project proposals. Now we have teams. Now we have 61 project teams. So if I use the same algorithm, we'd be here all day watching it slowly. Seeing your name appear. Agonizing over whether you're going to be on Tuesday or Thursday or whatever. That was my favorite part of the term. But especially one year we had. Someone came up to me before. He said, "I'm going to ICRA, so I need to present a week early." And I had the whole class believing that one unlucky person was going to end up having to present a week early. And people were like making deals with each other. It was great. But none of that this time, unfortunately. I'll just post. I'll run rand perm tonight and just post it on the website. Say tomorrow, okay? And it'll be fair. It'll just be run once. I'll take out the pause. But not as much fun. The other thing is, I have been trying to help everybody with their projects. I think I'm super excited about how things are coming. I've been prioritizing that over the notes. So I apologize that the notes haven't been there, but I do want to say that I'm going to be, as you guys finish your projects now, I'm going to be finishing the notes. I hope my goal is that by the end of the term to have something that you can look back at and have everything we talked about here. None of the chicken scratch all replaced with text. So I hope you'll look at it at the end of the term and decide if you want to use that as a reference going forward. But my plan is to finish it's much farther than it's ever been, and I'm going to try to finish those this term. So, all right, good. So we lost one lecture because we have 61 project groups, and I've only ever had 20-some project groups before. So today I'm going to try to give you some of the key ideas from stochastic and robust control, but it's going to be a window into things you can learn more about. And I'll put a little bit more detail. I'll put the 2 lectures worth in the notes, but you could take an entire semester course on either one of these topics. So I'm just going to hit some of the big picture ideas, and maybe I hope that I can connect what can be a hard to penetrate literature with some of the ideas that you're very comfortable with from this class now. So that if I accomplish one thing, I hope that you'll see the connections by the end of this lecture. Okay, so stochastic, some topics, select topics from stochastic and robust control here. Okay, so let's start with the sort of the average cost optimal control idea. So so I said that if we now have a stochastic system, if I write down my traditional additive cost function, this thing, now j is a random variable. If I have x dot has some random input, right? Now j is a random variable, so I have to somehow define my optimization better. And one of the ways that we can do is we can ask to minimize over u, over a trajectory or over state feedback, somehow minimize the expected value of j. And that's sort of the philosophical choice of saying that I care about getting the best performance on average, and not worrying for the moment about worst case performance. So the expected value computation works nicely with the additive cost formulation, and you'll see sort of straightforward extensions of the tools we've learned for optimizing stochastic optimal, open loop trajectories. For feedback control, I'll give you a couple key results here. You can do dynamic programming. There's extensions of sort of DP, trajectory optimization, even the verification that we can talk about with these sort of stochastic ideas. But I think the first skill is understanding if that's the formulation you want. And just to give an example, there are places where changing your objective from a deterministic optimization problem, let's say I'd like to find a trajectory which just ignores stochasticity and plans an optimal open loop trajectory or optimal feedback policy. It turns out if you model the stochasticity, in some cases you can get fundamentally different and maybe more appealing, more robust behaviors. So as a simple example here, this is the compass gate now walking on rough terrain. I showed you the rimless wheel walking on rough terrain before. This is work that Katie Bill did in her thesis. We were trying to study the sort of the formulation of stochastic optimal control on this hybrid system. So she actually solved these problems with a very clever mesh discretization, but with basically a dynamic programming approach. So lots of computation, came out with optimal feedback controllers for stochastic terrain. It was the terrain wrapped. It was like the robot was walking around a huge amphitheater. So there was a finite discretization, okay? But one of the things that was a clear story that came out, well, there were a couple of nice stories that came out, but one of them was you could watch the robot's behavior as you changed the variance of the terrain, roughly. I mean, we drew the terrain out of some process. If you think about sort of the magnitude of the noise in that process, when it was flat, the robot had its characteristic compass gate, and as it got more and more robust, you could see a qualitative difference in the way the robot walked. If you told the robot that the terrain was rough, it would take a much more conservative gait, which when you're a two-legged stick walker, conservative means you swing your leg forward like this, and then you come down, it's very inefficient. The objective, I should say carefully here, was to maximize the distance that you walked before you fell down. So just like the rimless wheel, you'll eventually fall down, potentially, but you'd like to maximize the distance you walked. So the flat walker would just walk fast. That was at a finite number of steps, too. So it would just walk fast with nice steps. The other one would trade off and walk fundamentally in a more conservative way, trading off the distance it could take on each step, but not falling down. So you really can get qualitatively very different things out of this. Another really interesting story that came out of that actually was that if you told the feedback design about only the terrain that was coming up for the next, let's say, 2 steps, and not the whole amphitheater, then actually the controller that optimized the performance for just 2 steps and then pretended the terrain was flat afterwards was basically indistinguishable from the one that had full information. So that's not too surprising, but it was nice to say it falls out. And that's sort of, maybe you'd think that when you're running across boulders or something, when you're hiking up in the White Mountains or something, you're probably not planning the next 40 steps that you're going to take. You're doing something just for a step or 2, right? And maybe that's because of your limited computational abilities. But actually, I think that if there's some fundamental time constants of stability, and there's some fundamental time constants of the noise, and really it doesn't matter. Only planning a few steps is all that really matters. Your stability can override the effects of noise in just a few steps. So that's another sort of, all these things intuitively can fall out of the process of designing stochastic optimal controllers. But the brute force approach that we took on this isn't going to work for a system that was much more complicated than this. This was basically roughly at the limits of what we could do with a clever discretization. Okay, so you can do, like I say, you can do things like trajectory optimization with stochastic inputs. You could imagine the simplest case being I'll optimize a trajectory, but every time I evaluate my trajectory, I'll simulate it with a few different random variables. And I'll take the average of those and try to make an update. Or you can imagine things like that. I won't go into the details of that. I want to make sure that you'll at least understand one of the core results, which is what happens if you have stochasticity and you add it into your LQR formulation. I want to make sure you at least get that part of the story sort of clear in your head, okay? So let's look at the special case of linear Gaussian system with a quadratic regulator. Okay, so problem formulation, we'll keep it in dt. In general, you could have another b. I'll call this b sub u and b sub w. Okay, but I've got some noise input. Let's say this is Gaussian IID. And we're going to take J to be, in the end, we'd like to get infinite horizon out. And we want to minimize the expected value of J. So what do you think is going to happen with this formulation? Some of you might know the answer, so don't say it. But first, let's just think about what you'd expect. What would you expect J to look like, the cost to go of this thing to look like? Right? You can remember the linear system. You could think of it as a quadratic potential, right? A ball running down the quadratic potential. Maybe it's high dimensional, but and you know, if I'm lucky, all this linear optimal control stuff will come out with a linear feedback, you know. So hopefully that'll work. Seems plausible. But what do you think about J? What would you expect your cost to go to look like? Quadratic, something more complicated. If I start here and I simulate this thing for an infinite number of steps, accumulating cost the whole time, what's going to happen? I'm going to get infinite cost, right? I'm going to get infinite cost because in the deterministic case, I could drive the system to 0 and it'll stay there and my cost stops accumulating. In the stochastic case, I'm going to drive my system, even if I get here, I'm still going to get bounced around forever, and I'm going to have some long-term stationary distribution like this, right? But I'm going to bounce around here, and my cost is not going to stop accumulating. So J is going to go to infinity, right? That doesn't sound so good. You could put a discount factor in, yeah, certainly. It turns out even if you don't, it turns out the optimal controller is still well defined, even if you don't. The cost is infinite, but it's actually, you can write down the cost as something that has this form plus some constant that goes off to infinity. Yeah? And in fact, the Riccati equation that you get out turns out to be exactly the same Riccati equation from the linear quadratic regulator, plus this extra term, which looks like the sum of the variance, the covariance, basically. That's it. I'll just set that to 1 to keep it simple. Okay. I. Yeah. And it turns out there's this sort of surprising result, which is that in the linear quadratic regulator with Gaussian noise case, the LQR gains are still optimal. If you put a discount factor in, you get something slightly different, but it's not. It's easy to compute. But turns out the result that everybody leans on is that LQR is actually the optimal stochastic regulator also. Okay? In some ways, that's awesome. That's amazing. It justifies me ignoring stochasticity, right? I could just do LQR and everything's good. You could say it's one of the worst things that happens to control, maybe, because then everybody says, I don't have to worry about stochasticity. And then they forget that when you do nonlinear systems, then actually that's not true, right? In general, this is not true. This is just a quirky thing that happens in some sense in the linear Gaussian case. But even using the linear Gaussian case, there's sort of a nice example that I can tell you of how you might use this to your advantage and get a controller out that's a little different than you might have thought of originally. Okay, so here's a simple example. Okay, application. Imagine you have a UAV, unmanned aerial vehicle, in wind. Okay, so my UAV, for this purposes, is just some system that has inputs. I'll make it discrete time just to stay with what we're doing. Let's just say it puts its state as an output. Now it has an extra input, which is the wind that's coming in. W for disturbance, if you want to think of it. W for wind, that works okay. All right. So I'm okay for the purposes of this discussion with saying we'll linearize the dynamics around some operating point. So I'm sort of okay with this step. I think that'll still work for you in applications. What I'm not okay with, or what I think will not be a good, useful model for you in practice, is assuming that the W is IID, right? Right? What do I mean by that? So I think wind as a disturbance is a colored noise, right? It has some spectral content, varies with frequency. I mean, so if the wind is blowing 5 knots at time 3 seconds, it's probably not going, I don't know, -5 knots at 3.01 seconds, right? It's not the case that the wind changes at it has every frequency content, right? The wind changes more slowly than that. And that matters, especially when our UAVs are small these days, that matters. So the time constants of the wind changing matters. Okay, so what can we do? We still want to use LQR, but LQR only takes Gaussian IID inputs. There's a really simple, powerful idea, which is let's model the wind as a Gaussian IID process colored by a whitening filter. Okay? So there's lots of good wind models out there in the literature, but let's do this. This will be my wind disturbance here, okay? So I'll take my Gaussian random variable, and then I'll just put a smoother on it or something, right? This can be just a couple, it could be a first order filter, a second, whatever you find is a reasonable description for your purposes, right? And this will now look like a time averaged random signal. It'll be a colored random signal. And that actually, we've had some success modeling wind with low order linear systems. And this is a well understood thing to do. It's called a whitening filter because of its use in the other direction. But okay. So now let's build the following system. What I care about here is my linear filter plus UAV as a system, which now I can model as a Gaussian IID process going in, a controller going in, the state coming out. Maybe I have to wire this up in the right way, you know. But you can imagine a composite system, right, that has the linear model of the wind plus the UAV. And now I could do LQR feedback on this, and I'm justified in doing that. I've got a Gaussian IID input, right? So what I get out is some linear feedback, but this is the composite state. Which has the wind filter state, and the UAV state. Does that make sense? Yeah? So I've got one or two state variables in here, depending on how many taps in my filter, let's say, what order my filter is. So that's part of my state too. And the LQR controller, as designed, is a full state controller, so it's going to take the whole state of that whole dynamical system. Okay, so can I use that if I want to use that in practice, what that means is I'm going to have to build an estimator, which we haven't talked about, but there's lots of good classes on campus about building state estimators and the like. I'm going to have to somehow estimate online the state of my UAV and the state of the wind as described by the states of this linear filter. And it turns out in most cases that's still possible. If you have a reasonable model of your UAV, then you can you can back out by watching. I mean, it's basically the inverse of this filter, right? You can figure out what those states have to be to describe the system as the state of this filter as you're monitoring the the state of your UAV, right? And it turns out that can work. That can work pretty well. So folks in lab got to watch me run around seeing if I could find the videos in the last minute and a half before lecture, but got one at least. Okay, so this is Joe's prop hang with a wind model. And the point is that it doesn't leave very much, hardly at all, right? So he sent me 4 videos. I'm pretty sure this is the one with the LQR plus wind feedback, but it was like a minute and a half ago. So, but the clear the clear message is that it does work as advertised and is slightly more compelling because I know because things are labeled. I found in his thesis here. Here we go. So he did this for perching outside. Okay, and oops, wrong one. That's awesome. The perch is right here. Okay, if you don't have the wind state, the wind can blow you around and you can miss. You can still miss with this one, but qualitatively, even quantitatively, adding the state of the wind can make a big difference in practice. All right. So that's a just a simple example of using the fact that we know the LQR result to give you something that's a little bit more than saying you should do the same thing as the deterministic case. All right, so that begs the question, can LQR, oh, sorry, go ahead.
Yeah, so when you linearize the original nonlinear stochastic system, how
Yeah.
do you get BW?
How do you get BW?
Yeah.
So it's just, I mean, you have to write the dynamics down. X dot equals f of x, u, and w. Partial f, partial w gives you BW. Yeah. Okay, so, you know, I'm not trying to say that, that LQR will do everything for you. Hardly that. Certainly there's the nonlinear case to think about. But even if you have a linear system, there was this sort of there was this rebuke by the community of people saying, you know, LQR, LQG is amazing. You can solve all these problems. It's the optimal estimator for the Gaussian system. And then there was this great paper, which I thought it would be better to just pull the paper up here. In the Transactions on Automatic Control, right, in '78. Guaranteed Margins for LQR Regulators by John Doyle. You know the answer, right? This is often cited paper because its abstract is awesome. There are none, right? Right. So just to make sure you can see that, that's the abstract, right? So the point is that even though it is the optimal estimator in the stochastic sense, if you want to somehow guarantee that there's robustness in the system, LQR and LQG do not give you that. Okay, you're gonna have to do a little bit more work if you want to have some guarantees, some certificates for stability. And this was right at the birth of the robust control age, if you will. Okay, so let's talk about some of the extensions of this into robust control. Okay, so it builds very nicely on the topics we've already been covering in class. But let's talk about robust control with L2 gain minimization. Okay, I mean, we talked about the worst case analysis already to some extent. We talked about commonly Lyapunov functions. I think you have that in your head. But the commonly Lyapunov functions already are going to fail me for just additive Gaussian noise. So if you want to have some sort of certificate of stability, of robustness, but be capable of dealing with something as simple as additive Gaussian noise, then we have to go into the area, for instance, of L2 gain minimization. So let's think about how this builds on what we've learned before. So let's just think about the verification question first. So imagine I just have a closed loop system, if you will. X dot equals f of x w. So it's my feedback system. And I've got some w coming in like this. Right? We talked about the worst case analysis, right? You could do with a commonly Lyapunov function. Right? If I find a v of x with v positive definite, v dot negative definite for all w in some range of admissible w's, then I can say the system's stable. I can talk about convergence to the origin in the simple case, right? Okay, this is going to fail even for linear Gaussian additive noise, right? If I have my system, my linear system, even if the ball is at the origin here, there's some chance of it leaving the origin. Therefore, it's not decreasing at all times, right? I cannot find a V which will prove robust stability for a system with additive Gaussian noise with Brownian motion. Is that clear? Because if you think about the system, when x equals 0, I need for v dot at 0 to equal 0. Right? When x is at this origin, I'd like v dot to be 0, but it is not. There are values of w for which it's not 0. Right? I could have had a noise which knocked me away from the origin, which means instantaneously I'll go up, and therefore I don't have a Lyapunov function for all w. I have additive Gaussian noise. So we need to somehow generalize the notion of a Lyapunov function to handle this case. And it turns out there's a really nice, simple generalization of the Lyapunov function, but intuitively what we're going to want to do is we're going to want to say, I'm going to let v go uphill sometimes, okay? But I want to somehow still guarantee, I have to let v go uphill sometimes, hopefully downhill most of the time, but uphill sometimes, right? But I want to somehow allow v to go uphill sometimes, but still have something to say about the long-term performance of the system. So how can we allow v to go uphill and still say something? So we're going to generalize this. Let's say that v dot is going to be now less than some function of x and w. And I'll call this a supply rate. Right? So before I said that v dot had to be less than 0. Now I'm going to generalize that. If I chose s equals 0, then I have Lyapunov back out, Lyapunov analysis back out. So this is a strict generalization, is allowing some function to be here. And the question is, can I choose some functions s such that I still say something useful about the performance? Right? The intuition about the supply rate here is that I'd like to think about sort of disturbances as adding energy to the system. And I'm going to admit that if this disturbance is adding a bunch of energy into the system, v might go up. But at least when the disturbance isn't adding energy to the system, or not adding much, I'd like the amount that I go up to somehow relate to the amount of energy being shoved into the system by the disturbances. Right? Sort of. Right? If v is smooth and s is smooth, if I have this guarantee, then I can at least have some notion, something I can say about the long-term dynamics. I could say that if I look at the system later in time, let's say if I look at time t1 compared to time t0, right? That's going to just be the integral of my supply, right? Or it's going to be less than or equal to that. So I'm going to go up no more than the amount of energy I jammed into the system. So the question is, can I use that to get some useful guarantees out of the system? Turns out, of course, I can. This is, by the way, is the notion of a dissipation inequality. If I find this v that satisfies some, is less than some supply rate, right? It's called a dissipation inequality. And it's considered a strict generalization of the Lyapunov analysis. Okay, so here's a standard format. Let's say I've got W coming in. I've got my dynamics in there. And let's say I have some outputs of interest, which might be the state. It might be more than the state. In general, I'll say Z is some function of X and W. One of the things I'd like to say, we talked about L2 gain minimization. That was the section sort of title here. If I remember, one of the things I wanted to say would be something about the L2 gain of the system. I'd like to say something of this form. It's an upper bound for the L2 gain, I guess. And the supremum here just means the worst case W, and we're gonna restrict ourselves to something that have a finite L2 gain, so disturbances that have some finite energy. Okay, so I'd like you throw the worst possible. This is like a max over the signal, right? So if I throw the worst possible noise at me, I'd still like that the sort of total disruption of my output is somehow bounded multiple, bounded relative to the total amount of energy I put into the system, right? Take it into this side, right? That it's somehow less than gamma squared times the energy in the input, right? So smaller gamma is good. And if I could say that, that's a reasonable thing. Saying, when the wind's blowing not very much, my system's going to be basically stable. And when the wind's blowing a lot, I'm going to accept that the UAV might blow around a little bit, but I'm going to put a bound on how much the wind gets amplified into my system. And we can do this via a dissipation inequality. Okay? The trick is going to be choosing my supply rate. Right? If I choose S of X W to be W squared minus Z squared, then I'll be able to show that this is true. So let's make sure you understand that. So if I have a supply rate like this, if I can find a dissipation inequality, if I can find some function V, I need for now V dot to be less than that thing. And so I have to find some function V that satisfies this. But if I do find a function V that satisfies this, then I can say that this gamma is a bound on the L2 gain. Okay, so to convince yourself of that, you could say that this thing gives me, that implies that V x at time t minus V x at time 0 is less than the integral. Take the gamma squared out. And that's got to be true for all W, right? That was our definition in the dissipation inequality. This thing had to be held for all W. Since this had to hold for all V, for all X, I can just choose X0 to equal 0. I can certainly make this 0, right? So it has to be true if this is 0 still. This thing I know is going to be positive. V is positive definite, so this thing is going to be greater than 0 or equal to 0. So so the ability to find this function V, which satisfies that equation right there, means that I must have proven that integral of z squared dt is less than or equal to gamma, right? I want that to be mysterious. The only way I could have found a v dot, and I haven't told you how to find the v dot, but if I did find a v dot, it must be the case that this is true and that this is that gamma is an upper bound on the L2 gain. Okay, this might be overly difficult to find a v this way. Right? It might be harder than proving that some other way. It turns out it's a convenient way because it gives me a pointwise, just like the Lyapunov function, right? So the magic of the Lyapunov function could be conservative, but it allows me to check a pointwise condition. I just have to check instantaneously, am I going downhill on this function, instead of having to integrate over the entire solution of the trajectory, which is hard. Same things here. This is conservative, right? But if I can show everywhere that I'm going down, compared to this supply rate, then it implies the bound I was hoping for, which is that gamma is an upper bound on the L2 gain of the system. Okay, now you can see why I like this, right? So this is just like Lyapunov analysis. You want to prove an L2 gain stabilization, you search for V. You can do that. Of course, you're going to see some special cases in the linear Gaussian kind of world where we can do that exactly. And you're going to see you could do it with sums of squares if you wanted to do it for polynomials, or you could do it with other techniques if you wanted to. All the tools you have at your disposal are going to work again. And now you're going to give some sort of robust certificate for a system with noise coming in. Cool, right? The most famous example of this is robust control, sort of H-infinity control, right? How many people feel like they know H-infinity control? The people who have taken 241 should say yes. Otherwise, I'm telling Sasha. But even if you've seen H-infinity, honestly, okay, let me write it down. But just everybody, how many people have seen H-infinity and sort of know that it exists? Yeah? So how many people know what H stands for?
Hardy space.
A Hardy space, right? It's a Hardy space, which is a concept from complex analysis, right? It's a Banach space. I don't know the full complex analysis story of this, okay? But the point is, there is beautiful mathematics that underlie H-infinity, and there's fantastic mathematicians that study H-infinity control, and the problem is that you can't read any of the papers, honestly. It's really, really hard to get your head around it when you start. Okay? So the Hardy space is roughly, it's from complex analysis. Here it's meant to imply it's a space, for instance, on the unit ball, or here it's meant to be the set of all stable linear systems. Okay, and then the system infinity norm, that's where the infinity comes from, is sort of the maximum system gain over all disturbance frequencies. That's not the point of the lecture, but just so you know where the name comes from, right? And if you love math, there's plenty for you here. Okay, so there's beautiful mathematics lie within here. Okay, so my goal is not to convey that whole treatment. I couldn't, certainly not in a lecture, but I want to give you the connections from what we already know in class. I think there's a couple of simple things I can show you that will connect you to all that literature, right? Oops. We'll use that dissipation inequalities to give the simplest sort of H infinity result, okay? The picture you should have in your head, which is one that you'll see over and over in the robust control world, is that, well, this is the first half of the picture, really, is sort of the picture I started with here. Let's restrict ourselves to linear control. Okay, and one of the H infinity design problems is to design K. We can minimize the L2 gain. And that is hard to do exactly, but we're going to push on an upper bound. Using the dissipation inequalities, okay? So how do you design K to make the gain from W to Z be as small as possible? I mean, one of the reasons that, one of the things I don't like as much about H infinity control is that it's beautiful and good to go into the frequency domain, but most of the treatments of H infinity live in the frequency domain, and I think that's harder to relate to the nonlinear systems. There are a few treatments of H infinity control that use Riccati equation techniques, time domain techniques, and those connect more directly to the way we've designed LQR so far. So I'll give you one of those. I also think there's more hope of them extending to the nonlinear case. Okay, so here we go. X dot equals AX plus BU. Call it like that. Now I'm going to do a slightly strange looking cost function here. I'll do my normal quadratic cost. Okay, but I'm going to add an extra term in here, or rather subtract a term in here. Intuitively, you could say that makes sense. You could think of this term as rewarding a small response to large disturbances, right? Small response over here. Mm-hmm.
Why does it matter if you put it in your model?
because I want to, I'm going to, it's the same notion of the supply rate and dissipation inequality. I want to allow that my system's performance depends on whatever W is doing to me, right? And then what I'd like to do is somehow solve a minimax problem, right? I'd like to minimize over U the worst case cost over W for J. Right? You think of it as a differential gain or something, right? And that's hard in general. It turns out this is one special case where we're going to be able to do something reasonable with it. Okay. Let me try to convince you. Okay. So if I write out the HJB for this, let me just set Q and R to 1 just to keep it simple. It's time varying, so I have that extra term. Expected time. I'll use the field's standard trick of choosing a quadratic cost to go. Now you might see where I'm going with this, but I'm going to try to see if I can take a maximum over W first, see if I can get rid of these guys here in closed form. Okay, so how do I take max over W? Well, if you look at how W enters here, it's a quadratic. Now it's a concave quadratic by definition, so gamma here is greater than 0. Okay, so when I plot it as respect to W, it's a concave quadratic function. I've got a linear term on W from this. I've got a quadratic term on W. This thing is positive, but negative of it is going to be now an upside down bowl. Okay, it's concave quadratic. So again, I'm actually going to be able to take the maximum over W easily by just looking at where the gradient vanishes. And that'll give me my peak, right? Take of that whole thing, figure out where the W equals 0, and I get you don't have to write down all this, but I get something that doesn't depend on U, okay? And I can solve for the worst possible noise, right? This is the worst possible disturbance. Okay, you should think you should think about what happened here, right? Why isn't infinity the worst possible disturbance? Because I've artificially rewarded myself for handling big disturbances, right? So by putting this into the objective function, that means big disturbances actually make me feel good about myself, okay? So actually, by inserting that into the cost function, there is a uniquely bad disturbance, which balances its effect on this, with the reward I give myself in the cost. If I stick that back in, I can now minimize over U, And guess what? I get back a familiar linear feedback. I said R to 1, otherwise it'd be exactly your LQR feedback. But S is different, right? S is now the result of this differential game, but it's still the best thing to do is to go downhill on my cost to go. Okay, and then the big question is, can I find an S, right? So all this looks simple and good, but it all hinges on the idea that I can find an S that proves this is true. Right, I also assumed in here that S was positive definite in order to take some of these, right? It's symmetric. You stick this all in, you get yourself another Riccati equation. Okay, a differential Riccati equation. You could take the infinite horizon case, give yourself an algebraic Riccati equation. And it looks almost like the original Riccati equation. So with Q equals 1, it looks like this. Okay, it's almost identical to the LQR Riccati equation, but there's an extra term sitting in here with the effect of the noise. And unlike the algebraic Riccati equation from LQR, I cannot guarantee for you that this thing has a positive definite solution. You pick a gamma, you tell me B, I may or may not be able to find a positive definite solution. However, all that beautiful mathematics that people have done, there are strong theorems that tell me something about this. Okay, if I take gamma, gamma only makes sense, you know, sort of from 0 out to infinity. Well, first let's look. If gamma is infinity, then this term's 0. This term has no contribution, and I'm basically going to get on my LQR controller. So we're actually, I'm sure that the Riccati solution, because the Riccati solution reduces to the LQR Riccati solution when gamma equals infinity, I know that there is a positive definite solution when gamma is equal to infinity. Okay? At 0, it doesn't mean it's sort of nonsense. Okay? There's strong theorems which tell me that there is some place, there's some scalar gamma for which there is a positive definite solution. If there's a positive definite solution for gamma, there's a positive definite solution for everything greater than gamma. That's just something you have to believe me for right now, but I can point you to the theorems. Okay. But if you can find a gamma where this thing has a positive definite solution, then you're good. Okay. Everything greater than that has also got a positive definite solution. And below it, there will be no solutions, right? So this thing is sort of only exists at some critical point. So in practice, what people can do, what you do as an algorithm, is you can do a line search on gamma. Okay, I'm going to say, it turns out, especially in the time invariant case, solving the Riccati equation for a particular gamma or finding out if there's a positive definite solution is numerically easy. Okay, so you say, all right, I'm going to prove that this thing has an L2 gain less than 2. You give it to MATLAB, and it says, sorry, okay, L2 gain less than 4. Got it. All right, so now you do a line search, and you do a bisection search and try to find exactly what your L2 gain is, and I get out, you know, L2 gain of 3 is my minimal possible L2 gain that I can prove, right? And you get out a controller, which you get the Riccati equation that comes out. You get the cost to go function of that minimax problem with the gamma set to that particular number, and you get a controller now, which is related to that cost to go. Okay, so you can do a line search on gamma.
Is there a way to do like a finite gamma?
I think it can be arbitrarily large, but I think there should be one. Yeah, because you approach the algebraic Riccati equation, the LQR Riccati equation. But that's a subtle. I'm not sure for that. I mean, I don't. But I mean, so it assumes that the system's stabilizable and all the LQR assumptions.
Yeah.
But I think so. I mean, in practice, the algorithms search up until they find it and come back down. Okay, once you have a gamma where there's a positive definite solution, then it can be shown. It's not trivial to show, okay, but it can be shown that J, my cost to go now, is a dissipation inequality, okay? That J dot is less than, it goes downhill on my cost. It's not too hard to believe that that's possible to show, but showing it involves looking carefully at the maximum, and I think it requires some extra work that's special to linear Gaussian systems, but okay. That means J is a dissipation inequality. Right? And if you think of it as, you think about your Z output as the vector like this, then Z transpose Z is just X transpose X plus U transpose U. And you should just think of this as the Z that we had before. So the gain from W to this Z is less than gamma. Yeah, what's up?
Is there a reason you're saying that dissipation inequality holds true for all X and W, but not W?
Well, U is implied by X. U is a function of X by negative KX. Good question. Okay. So what just happened? So, if you've seen H infinity before, I hope that feels like sort of a well-connected version of it. It connects sort of back to, compared to most treatments, it's much closer to LQR than you'll normally see. In practice, what it means is that for just a little bit more work, I solve just a slightly different Riccati equation. I can get out a controller which minimizes an upper bound on the L2 gain, but has some guaranteed robustness, right? That I can actually give you a certificate when I'm done saying the gain from the noise input to the output I care about, which I've chosen to be XU here, but you can choose richer things, is bounded by gamma, right?
So how does that gain from this H infinity LQR compare to just like the regular LQR type norm? Trying to get this certificate. What does it actually do?
So as you change gamma up, you can get LQR out. So I actually spent a little time. I took the cart pole LQR and I tried to come up with a clever input description of the input output uncertainty, because you can think of I'll draw this more carefully, but you can treat a nonlinear system as a linear system plus some disturbance. You could say my dynamics are linear plus the difference between my linear system and my nonlinear system are the disturbance. Okay, and you could try to build a controller that has, let's say, a bigger region of attraction. I couldn't do it. I couldn't do it quickly this morning. But you know, probably because we tuned the LQR controller so darn well, right? But and in fact, yeah, I think really for this you could always. I'm not sure can you always, but I think you can. I mean, effectively, you could choose a different Q and R that might give you the same controller. I wonder if that's always true. That might always be true. That you could just choose a different Q and R. This is certainly a different way to express the uncertainty. It might be a more natural way to express your goals for the control is to be robust to the particular type of uncertainty. I think the big qualitative difference is that I can give you a certificate when you're done.
So it's a way to get the guarantee, right?
I think if I spent 2 hours on it, I probably could have given you a bigger basin. But the ones I tried quickly had the same basin. Yeah, which is a subtle thing because it could have been because the Riccati equation that came out was a little bit more, numerically bad for the sums of squares. There's a lot of things going on in there. So, but there are some cases where it makes a big difference. I just didn't find this one.
Is there any relationship between gamma value and the variance of distribution of trajectories of control system?
You want to say that the distributions on X, the stationary distribution, let's say on X.
Even if we compute a control input with quality system, we will have a stochastic system where X is a random variable.
Yeah. I think the answer is definitely yes. I mean, I think that.
Robust control seems to me we are not only regulating the average case, but also the distribution of trajectories.
Yes. So that's exactly right. So if you what it's telling me is that it's the integral solution, right? Which is cool. You're talking about the long-term solution. But basically, if you give me a small disturbance input, I'm guaranteeing that over the long term, I'm give you a small distribution back out of states. That's exactly what it's saying. And there's a scalar, multiple on, with some z being x plus u. It's not quite as simple as a mapping from w to x, but it's basically saying yes, that the energy in w gets scaled to some extent to the energy in the stationary distribution of x. That is the right way to think about it. And you're hoping the gamma is small so that maybe you're dissipating W quickly, right? So absolutely, it should give you a bound on that. In this particular case, the simple to derive example where you can do the minimax, I have to have U in my output of interest. If I took U away, my R was gone. I wouldn't have been able to do the same derivation. So it's.
U just help you because it's additive, right? We end up with like x squared plus u squared on the left-hand side, so just integral of like 1x squared.
Yes. That's absolutely right. But it gives me a well-defined control. Yeah. Yeah. Okay, does that make sense? Yeah.
So I'm trying to interpret the W star.
Yes.
When you write U, like it's the thing that's going to push you up your cost function the most.
Yes.
So it's like an instant. It's the.
Oh, you're the picture of going uphill.
Right. It's the thing that's going to make you go the most uphill.
Exactly.
Cost function.
Yes.
But it seems like I'm having trouble reconciling the fact that like H infinity is like usually the frequency treatment, and it's like maybe your system has like a resonance or something, and if you get noise at that resonance, it's going to blow up. How do you? This is like an instantaneous kind of like instantaneous.
It implies the long-term bound, but this is instantaneously the worst. You're right. Yeah, and I think the reason there is going to be a disconnect between the frequency domain and U is that this is a particular instance of H infinity where I've chosen Z specially to have X and U coming out so that the mapping works out, and I can give you an LQR-like derivation, right? So you're not going to be able to see everything from H infinity through this derivation, right? But it's the one that I think can land, we can understand. Okay, so let's think about how you might put that to use as we wrap up here. Okay, so there's a second picture that you always see on robust control, like on the cover of the textbook or whatever, right? So you have your plant You have W coming in, Z coming out, X coming out. This is the picture I drew for you just now. There's another half of the picture, right? Okay, sometimes it's reasonable to model the disturbance input as some scalar multiple of the output of interest. Okay, so this is really the case. Do you remember before I wrote, I did this sort of, there's the gain uncertainty case where you can have your fixed point. This is now the third time I've shown this, because I worked hard on it, right? But, right, that's the multiplicative noise case. The additive noise case is hard, you don't have a fixed point, right? But the multiplicative noise case is special. Your fixed point stays the same. It might change your region of attraction. Okay, so this picture that I'm drawing here is the multiplicative case, right? Where I can write the noise coming in, the disturbance coming in, as a multiple of my output, Z. Okay, so in this case, there's hope of, so for instance, I could write this now as A plus delta A X B plus delta B U, if you want, for instance, right? Where this is somehow my deltas, right? Okay, so when you do that, then there are more tools at your disposal that you'll find in the robust control literature. So it's possible to recover basically a robust stability, right? Not just a gain. I could actually get out something that drives my system to zero. And the key theorem that lives in there is the small gain theorem. Okay, so for instance, say I have x dot is sine of x. I could approximate that as a linear system plus some gain, right? Somehow between those two at all times for, in some range, I can give you some sort of a gain bound on what the nonlinear system's doing in terms of a linear system, an uncertain linear system, right? You could potentially try to jam that into this framework. And the basic idea is that if I can get the L2 gain of this guy to be less than 1, and the L2 gain of this guy to be less than 1, then the loop gain will be less than 1, and I'll recover robust stability. Okay? This one you're choosing as a modeling parameter. I could always, if your robustness thing has a gain of 10, then that's no problem. I can just multiply. I could turn that into I could absorb that into Z. Okay, so typically you just take this, scale it so that it's less than 1, and then you try to do L2 gain minimization of your plant through controller design to minimize the L2 gain across here. If you succeed in making the total loop gain less than 1, then you have a certificate of robust stability. Okay? Okay, so I know that's hopelessly shallow treatment, but let me just, I mean, people are still working on this. This is Hung Kai's work. Some of you have met Hung Kai, and we're still working on L2 gain optimization for walking, for instance, trying to use the height of the terrain as the unknown disturbance. You know, Hung Kai showed some nice algorithms for computing the L2 gain across a limit cycle with numerical techniques that you would recognize. Okay, and the point is, so he's able to compute them using semi-definite programming for simple systems. This was the most complex system he got a year ago, 5-link walker, just to give you a sort of sense of where we were at least at the time. And if you look at sort of the robustness of the resulting controller compared to LQR, this is designed a nominal trajectory and you're just trying to stabilize it. You know, the L2 gain minimized, the one that was explicitly had a feedback controller that was trying to minimize the sensitivity of the gate to the rough terrain, walks many, many more steps than LQR stabilized. Okay? I mean, I think it's a good result, but I think we're just starting to be able to apply H-infinity type techniques to the kind of robots that we've been talking about all semester. Okay, so we'll send out an announcement when we post the rules. I'm sorry you didn't get to watch your names appear slowly, but it's good. I'm looking forward to it.